This video is for lesson 11-4. I'm going to do a little bit more with the congruence criteria. Learning goals are to apply the congruence criteria to figures on a coordinate plane. And let's prove the AAS criterion and create a criterion called HL. We can use the triangle congruence criteria on the coordinate plane. So here's question 1. Greg's boss hands him a piece of graph paper that shows the plans for a truss. Greg's boss asks him if he can prove that triangle DBE, so this triangle here, is congruent to triangle FCE, and that's this one here. So because this is on coordinate grid, Greg can find distances by counting the units. If they are horizontal or vertical, then they're very straightforward to count. And if they are diagonal, then we can use the Pythagorean theorem. So question B, let's find BD. So the distance between B and D. Horizontally, that's 3, and vertically, that's 3. So with the Pythagorean theorem, we do the 3 squared plus 3 squared is 18, and then a square root. So the answer is the square root of 18. Let's find DE. So that's just straight across here, and that's just a matter of counting the units. 1, 2, 3, 4, 5. That's 5. BE, with the Pythagorean theorem, is the square root of 13. Now over on this triangle, when we find distances, we get those same results, the square root of 18 and 5 and the square root of 13. So question B, can Greg use this information to prove that they are congruent? Yes, he can. He can use SSS as his justification. Now in number 2, in item 5 of a previous lesson, we discovered that there was SSS, SAS, and ASA, and that there was another one that worked called AAS, but we hadn't yet proved that that worked. So what does the AAS congruence criterion state? Mark the triangles below to illustrate what this abbreviation might mean. So this means that 2 angles in the first triangle are congruent to 2 angles in the other, and that the non-included side is congruent. So not this side here, but either one of these other sides. And I chose to put the mark here, and then on the other triangle to put the mark here. This is showing angle, angle, side. Number 3, the proof of the angle, angle, side criterion follows from the other congruence criterion. What that means is we're going to use those other criterion that have already been proved to be true as reasons in a proof for AAS. And once we prove that AAS truly works, we can then use it for the rest of geometry class as a reason to know that triangles are congruent. So let's start with 2 triangles and some given information that creates that angle, angle, side situation. Angle, angle, side. That's what all this given is providing us. And let's prove that these triangles are in fact congruent. So first statement, we have these 2 triangles. That's given to us. Next statement, the sum of the angles in the first triangle, angle M, N, and O, adds up to 180 degrees. And the sum of these 3 angles in the other triangle adds up to 180 degrees. That's a fact about triangles, that the 3 angles of all triangles add up to 180 degrees, and it's called the triangle angle sum theorem. Okay, next, because those angles add up to 180 and these angles add up to 180, we can say that those angles are equal to those 3 angles in the other triangle. If they're both equal to 180, then they are equal to each other. That's the transitive property. Okay, next let's copy down some more of the given information. Next step, because these are congruent, their measures are equal. Because these are congruent, their measures are equal. That is the definition of congruent angles. That's what it means to be congruent. Congruent angles have equal measures. Okay, next step, let's go back to the equation that we had in step 3, right here. We have on the left side the measure of angle M, N, and O, and equal to on the right side the measures of angle P, Q, and R. And then let's create in this next step, step 6, a new right side of that equation. We're going to replace angle Q with something that's equal to it, angle N, and you see that here. And let's replace this part here, the measure of angle R, with something that's equal to angle R, which is angle O, and you see that filled in right here. That's the substitution property when you replace things with other expressions that they're equal to. Okay, step 7. We have a algebra equation. Remember, these are measurements, so these are numbers. So this kind of looks strange, but this is simply an algebra equation with numbers in it. And I noticed that the measure of angle N and the measure of angle O are on the left side of the equals, and they're on the right side of the equals. So let's subtract them both from both sides of the equation. And that leaves this equation. That's the subtraction property where you can subtract things from both sides of the equation. Next step. If the measures of two angles are equal, we can say they are congruent. Again, that's the definition of congruent angles. We had used this earlier in this same proof. There was one more piece of given information that we hadn't yet written down as one of our statements, and so you see that here. Then we're ready to conclude that the triangles are congruent because we have a pair of congruent sides and a pair of congruent angles, and then much earlier we had another pair of congruent angles. We can use angle side angle as our reason. So we had this situation where we had two triangles and the information given to us fit an angle side setup, and we proved that they were congruent. So now we know that that angle side setup is enough information to know that triangles are congruent. Number 4, below are pairs of triangles in which congruent parts are marked. For each pair of triangles, name the angle and side combination that is marked and tell whether the triangles appear to be congruent. So here we have a side with a mark, a side with a mark, and an angle. And I notice that the angle is not the one that's included between the sides. And so this was that side angle situation of a couple lessons ago. It was one of the 6 things that Greg investigated, but then discarded and said it didn't work every time. We even talked about this, that side angle could be written as angle side. You remember that? And I made a joke that we don't use that one in geometry. Do these appear to be congruent? Yes, they do. Okay, question B. Here again we have a side, and an angle, so SSA. Do these appear congruent? No, they don't. And again, a couple days ago, that's why Greg discarded SSA as being one of the congruence criterion, because it didn't always guarantee that triangles would be congruent. Question C. Again, based on what's marked with these little marks, we have SSA. Yes, they do seem congruent. Question D. Again, we have SSA, but no, these triangles don't look exactly the same shape. They're close, but not quite exactly the same shape. And so this one is no. Okay, number 5. We know that in general, SSA does not always determine congruence. However, for 2 of these cases, they did appear to be congruent. What did the congruent pairs have in common? So that was the one from A and the one from C. What do these triangles have in common? Do you see the right angles? These are right triangles. So when they are right triangles, it looks like that SSA does guarantee congruent triangles. So number 6, the last one for the video. In a right triangle, we refer to SSA as hypotenuse-leg and use the abbreviation HL, not the abbreviation SSA. Write a convincing argument in the space below to prove that HL will ensure that triangles are congruent. So here I have 2 right triangles, and I have the hypotenuse congruent to the hypotenuse in the other. And we have that one of the legs is congruent to one of the legs in the other. And these are right triangles, so I have the 90-degree angles marked. So I think, as an argument of why this would work, that if we use the Pythagorean theorem, we could show that BC was equal to EF. And then we have all three sides of one triangle congruent to three sides in the other, so they are congruent by SSS. So here is my argument to prove that HL is one of the congruence criteria that works. Here are some check your understanding questions, so I'll pause the video. So in this lesson, we used those congruence criteria that we had developed, but the figures were on the coordinate plane, which allowed us to count units, or if they were in diagonal arrangements, to use a Pythagorean theorem to find distances. We also proved that angle side is a legitimate criterion, and we developed one called HL that you can use with right triangles.